Good morning, everyone, and welcome to day number 4. To wake you up and start with, I would like to repeat some important aspects we have discussed yesterday in the context of phosphor thermometry. So as I explained, phosphor materials are ceramic, and these ceramic hosts are doped with metals, transition metals, for example, like europium. As we have seen, there are many different choices. So they're doped by ions, which are then the materials that actually show a certain sensitivity with respect to temperature. So the temperature sensitivity This temperature sensitivity is in terms of the spectroscopic properties. And we have seen that there are different choices depending on the phosphor. The most robust methodology is the decay time method, and we have for that reason looked into some more detail into this method. And the idea is as follows. You have a surface. This surface is coated by a very thin film. This film contains the phosphor material. The most easy way to do that is that you do an airbrush coating, meaning you have a high temperature resistant binder in which you put this powder of phosphor material, and then you use a laser in the UV typically to excite the phosphorescence, and then you do have here a detector. It can be either a CMOS camera if you have a field, or a PMT, a photomultiplier tube if you just look pointways. However, the detector must allow for a temporal resolution. That is, you have here the intensity of the phosphorescence over time, and with a good discretization, with time 0 being the instant where the laser is fired. If you use a Q-switched laser, it is like a delta pulse in this temporal domain we're looking at, because the decay of the phosphor is in the microsecond or sometimes millisecond regime, depending on the phosphor we're after. And then eventually you see here a decay that is, at least for some phosphors, in a certain range mono-exponential. And the idea is then, after fitting, that you receive here a decay constant, a decay time, which is representative of a temperature. And that brings us to the point that these phosphor thermometry needs calibration, and that is done in an oven where you have a controlled environment. You do the calibration against a thermocouple, and you end up then with something like this. You have here the decay time as function of temperature versus the temperature, and this is very often here shown because of the large variation in a logarithmic scale, such that you have a certain sensitivity with regard to temperature for a specific phosphor. And I've shown this specific for different phosphors, and I've shown that we have phosphors that are more for the low temperature range, but as well phosphors that are for the high temperature range, clearly above 1000 Kelvin. And so once you have this calibration in the real measurement, then you determine, hopefully with a good discretization, as I said, the decay time itself, and then you trace it back here over the calibration, or from that you determine then the temperature at this certain location. We have seen as well it's a semi-invasive technique because you have to coat the surface, and because of the properties being a ceramic material that acts as an insulator. And so you have to consider that maybe you come up with patterns or films that are not completely covering that surface. Let me give an example. When you have here a surface you're interested in, you could as well coat certain areas only, because probably your temperature gradients in these directions are not as large, such that it's sufficient to get these information spot-wise and monitor that with a high-speed CMOS camera. And thereby you would have in between then here all the normal metal, let's say, of your combustor, and thereby would influence the system not as strongly as you would if you would cover that completely. Yeah? Okay, so there of course are parameters to be chosen in dependence of your experiment and the question you're asking, and for the method, you can say, is adaptive to these different needs quite easily. If you of course do have strong gradients for whatever reason, maybe this way of coating is then not appropriate. Okay, we have discussed as well some applications, and to finish that chapter, I would like to share with you some recent results we have obtained by using this technique, again in IC engine, but here as well together with some flame front imaging to see how a flame, when it impinges, in this case at the piston, is actually increasing the temperature of this piston, to see heating rates. And so you see here again a sketch of this optically accessible engine, where you have here this piston head, which is made from quartz, where the temperature has been measured at this location somewhere in a certain area, in something like a thin stripe. And the phosphor has been, as you will see in a second, excited from below. And then as well the phosphorescence has been recorded the same way back through the piston. And simultaneously, and this was operated close to top dead center, where you have here only a small region, here laser beam for exciting OH fluorescence was sent in, such that we had a few millimeter stripe just in top of that piston to see the temporal development of a flame that came into the field of view and then eventually touched the surface of the piston. And so this was done temporally resolved. In that experiment we had available 3 pulses to excite the fluorescence. So in one cycle, 3 instants of the flame propagation during its approach at the wall, and with a thermography of the wall that has been as well taken in high speed over a larger range of crank angles. So the decay time methods has been used. Again, you see for this phosphor, this GGG donated with chrome, doped with chrome, but as well as some cere that has been added here to reduce the afterglow. So some of these phosphors do show at a certain time after excitation a long-lasting afterglow. And this afterglow can be reduced if you co-dope that with another material. And in this case, this was cere. And so by that, we have had here again a certain range where a mono-exponential fit or model was able to reproduce this waveform, from which we deduced the decay time and with the calibration done beforehand, the temperature. And that was then done with a high sensitivity and a reasonable signal to noise in the order of 5 Kelvin. And everything was done within 10 microseconds. This is sufficiently fast that you can repeat your experiment or your measurement of the temperature successively in the cycle for many times. So the experimental setup now getting a bit more complicated. Things are combined. You see here the sketch once again of the schematic of the engine. You see here at this location where the radiation for excitation of OH has been coupled in, very close over the piston. where we were mainly interested, of course, at that moment where the flame impinged at the wall, at the piston. And that means that was close to top dead center. So we were lucky that there were still some optical excess left, just a few millimeters, but sufficient to monitor the flame. And this is shown schematically over here. After ignition with the spark plug, the flame propagates, a turbulent flame propagates, and eventually it comes close to the piston surface, as shown here. And then the last few millimeters have been observed by exciting OH and monitoring the OH with these high-speed IRO in combination with the CMOS camera. Yeah? Looking at this very small light sheet. And simultaneously in the same cycles there has been used another laser. This was a high repetition rate UV laser where we were exciting then the phosphorescence from coming below. It was a very thin coating. We controlled that. When we produced it, it was in the order of 10 microns and very reproducibly coated. And then the phosphorescence as well was imaged in the same direction because there was no space left really to look from top on these coating. It was then traced back to this other high-speed camera. And here, of course, you see an optical element that must be beam splitter. So UV is reflected and the redshifted phosphorescence is transmitted. And by that, you have here in this schematic shown the excitation in, from bottom to top, and then the reverse way, the detection. The engine, of course, is an optical engine, and it's very critical in terms of thermic equilibrium. You will never reach that with this kind of engines because you can't operate them fired for a very long time, because then the system heats too strongly up and some of the components would be damaged. So the procedure that has been followed over here was that we have had motored cycles, and then after 300 of them, 100 fired cycles, and I've done that a couple of times, such that already the system and the surrounding was at a certain temperature. And then within the last 100 cycles, the data have been used for the data post-processing, as to be shown in a second. The idea was to have the phosphor thermometry in a certain crank angle range from -6.5 before top dead center up to 14.5. And the OH PLIF, unfortunately, we had only 3 images. They were placed with a distance of 1.5 crank angle to each other around top dead center. So this is then here the region where this data has been taken. Here you see the operation points as well. A drawback in this engine, in these optical engines, is that the mean effective pressure is limited. I think I mentioned that earlier this week. In our engine, that's roughly 10 bar. We have operated here, for that reason, only part load. And the system was operated with CH4, so a gas engine where the gas has been put into the intake port, so perfectly premixed, either with equivalence ratio 1, this is lambda, this is 1 over equivalence ratio, or for lean conditions. And then you see here the measured pressure traces, the mean for stoichiometric conditions, of course, higher in average than for the lean conditions, and you see with the dashed lines the variation due to cyclic variations. Okay, here's an impression of one cycle. In the upper part, you see the approaching flame as marked from this OH distribution, qualitatively, of course. With the spatial domain perpendicular to the piston spreading over this few millimeters, and along the piston surface here spreading over something like 25 millimeters. And those images are displaced from each other by 1.5 crank angle degree. And then you see the dynamics of the flame during the approach, where it then hits the wall. And of course, the flame is quenched, something I would like to discuss in some more detail tomorrow about flame-wall interaction. And there is heat transfer. And the heat transfer changes the temperature, and that is shown over here. In this direction, that's the same spatial domain, that is along the surface of the piston. And this direction is as well a crank angle. And what you see in color coding is the relative temperature relative to the first temperature distribution that has been measured, minus 6.5 crank angle before top dead center. So this is this black-blue. And these gray stripes denote the time when these 3 OH Pliff shots have been recorded, separated by 1.5 crank angle, as mentioned. And it's interesting to see now that at locations where the flame impinges first, you see as well with a certain delay that the temperature shoots up. It's not a big change absolutely, so in the order of 30 Kelvin, 40 Kelvin, but this is in a very rapid manner, such that the heating rate, if you refer that to a second, is in the order of 15,000, 20,000 per second. So the heating rate is very fast. Has anyone an idea why you have a phase lag over here? Why is that? Why is it not happening immediately? This is an insulator, 10 microns thick, and it's excited from below. And the UV light is partly absorbed, or strongly absorbed, I should say, in this coating, meaning that most of the signal from the phosphorescence here, from this coating here, is coming from the lower end. And that's why the heat needs some time to diffuse through. And that makes a certain phase lag. You can calculate that in the paper we just published, which is online now in Applied Physics B. We calculated as well the heat transfer with a 1D model, and by that, assuming certain properties for the phosphor coating, it could explain these phase lag, I think, in a correct way. When we're doing that and compare different cycles, here you see the cycles that have been recorded after the heat up. This was motored, fired, and then finally taking the data. For these different equivalence ratios, you see 2 things. First of all, the engine behaves reproducible in the sense that the heating over the cycle number is more or less identical from realization to realization, but you see as well the problem with IC engines with optical excess, you don't reach thermal equilibrium. And that is something which is difficult to change because of the construction of these devices. And that, of course, means that investigations where you need to have thermal equilibrium, I would say, for example, to study an O formation or something like that, there you have to be careful. So again, that brings us to the point that these engines are maybe better suited for early times in the flame propagation than processes that appear late in the cycle. Okay, using now these temperature changes, you can, as a function of the crank angle, measure now the temperature increase. As we have seen from the single shot, we are talking about something like 20 to 30 Kelvin. And this is now from many cycles that have been taken in corresponding locations during the heat up time, where you then see here phase average. This means related to the crank angle for these 2 equivalence ratios. And if you look at that, it's a bit strange if you see that the leaner case has a higher heat up rate. And so why that? Well, if you actually look where the flame impinges, that has been not considered over here. So all information has been taken without considering whether flame has been present at the wall or not. And so you can do better. Because of the knowledge where the flame appears, that has been here conditioned in the next step where actually the flame has touched the wall. These are highlighted here in these yellow bars. And if you now condition as well, not only on the face, but condition as well only at those locations where the flame has impinged, then you find a slightly different heating rate, where in most of the times, at least here, the heating rate of the lambda 1, equivalence ratio 1, was higher. But actually, it is not such a huge difference because the temperature gradient, of course, is different between these 2 operation modi. but it's not so large that the heating rate seems to be more or less identical. But it's interesting to see how the standard deviation has changed. This comes from the fact that if you operate lean, you will have a higher cyclic variation. You will have a stronger wrinkled flame, and that means as well that you find here a higher degree of variation. But overall, I would say the variation is very small. So that's very reproducible, such that from that data you can extract information that can be used for cooling, for example. And to lay out cooling systems in cylinder heads, and yesterday I mentioned that this technology has been transferred to car manufacturers, and I guess they make primarily advantage out of these measurements by coming up with better designs of cooling of cylinder heads. Okay, with that, we can summarize that chapter. So what I've shown is that phosphor thermometry is a method that allows you to either point-wise or 1D, like in the last example, but even measure surface temperatures in a 2D manner. We have seen that the decay time method is rather robust and precise, meaning that changes in your setup will not influence your calibration. That means an ex-situ calibration is possible. Yeah, you do the calibration in the oven and then transfer your measurement equipment to the device under test, and you still can rely on this calibration curve, which is not true for the ratio method, which is based on the average of two images. And we have seen as well that in especially the spatial domain, the precision of this decay time method is much better. We have as well discussed for the decay time method the possible sources of errors, systematic errors as well as statistical errors linked to accuracy and precision. And that showed that, of course, you can do many things wrong, but if you do it properly, you have the potential to come up with a accuracy in the order of a Kelvin. And the same holds true for the precision. It is a technique that can be applied to many different systems, and it's rather robust, as I already said, especially when you compare it to gas phase thermometry. It's much easier. And so for that, I think there's a really high potential for other applications as well. Okay, with that, I would like to close that chapter unless you have any questions.
In the previous slides, the plots that show their average cycles, right?
Their average of what?
They are average values for a certain number of cycles that we're measuring, right?
Yeah. The question, how many cycles? So the question was about these phase average and conditional average values. How many cycles have been used? Actually, I have to look that up again. I might forgot the number. This is in the order of 100 cycles. Yeah. You should not maybe do it with 10 cycles. That's too little. Yeah. So the best way to do that, a general answer again, is not good. What you should do is you should take initially a large number of realizations, and then you look for the convergence of your statistical moments. So you calculate the mean value, let's say with arbitrarily chosen values. You start with 10, you go then to 100, you go then to 1,000, and then you look how your mean value converge. And the same you should do for the RMS value. And then it's upon you to decide which statistical precision you want to have. Yeah, that's it.
But you are limited by the temperature that you can achieve on the optical engine also, right?
Say it again, you're limited by the...
As you are limited to 10 bar,
yeah.
You have a temperature limit also, right?
Yeah, the question is, because of the engine, of course, if there is any temperature limit, absolutely. Because we can't operate at full load, we cannot go to that regions where the cooling problem really appears. That is true. This is here limited to more proof of concept, and of course it can be used in conjunction with simulations to better come up with or validate models that predict that correctly. If you want to do that in an engine that is really operating at close to full load, then you have to do something different with the optical excess. And that can be done, of course. If you have resources, then you would do it differently and come up with a minimal invasive optical excess, where you then have more or less the full metal engine and only small bores, where you then have endoscopes that are or can sustain and survive even higher mean effective pressures, higher temperatures. Yeah. Actually, for the phosphor thermometry, we have done that. We have one paper out where we have shown how to develop such an endoscope. But still, you might end up with problems that come from a different side. For example, if you take a full metal engine with all the lubricants, yeah, you will have an oil film. And if this oil film is covering your phosphor, then you're in trouble, because that oil typically absorbs UV. And then everything changes. And so you have to make sure that these problems are somehow overcome. And that is very specific to the geometry and the system you're looking at. Okay. Yes, please.
On the same lines of the oil affecting the signal, so can these phosphor be used as seed particles for studying circulating flames?
The question is whether you can use these seed particles to study soot flames, you said?
Flames which are already having soot.
Which are already having soot. Well, these people have tried and succeeded with that to put these seeding particles into the fluid flow. There's as well one poster from Chris up there. These phosphor materials that are useful for this kind of investigations are limited to temperatures maybe up to 900 or 1000 Kelvin. If you want to do that in a flame, still we do not have any seeding material that is for that purpose well suited. And so if you're referring to flames right now, we cannot measure the temperature based on seeded phosphor particles in such a flow. Up to 900 Kelvin or so, that has been demonstrated with a certain precision and accuracy, of course. Okay, yeah.
So if you're saying the engine oil actually affects your measurement, can you actually measure then also the engine oil itself, or is that
so the
temperature film, for example, of the engine oil, or how much fuel dilution do you get from the temperature change when the fuel hits the wall?
So the question is whether you can make use of the, you mean that you still have a phosphor coating at the wall. You're not talking about doing phosphor particles into the oil.
Well, either or, actually, now when you say it.
The problem is when you have an oil film and that covers your phosphor coating, then the laser doesn't penetrate through that film. The film might have, I don't know, 30 microns or something like that, and nothing will be left to be for excitation. And so that is changing the signal down to zero. If you would like to measure the properties of the oil film itself, it's maybe not necessary that you put any particles in, but use the fluorescence of the oil itself. That is maybe a choice. But measuring the temperature of that film is a different story.
Well, of interest is actually the fuel dilution in the oil film, specifically in the rectangle area. So if you can actually make an assumption about that from a temperature side, that would be of interest, let's say.
Of course, I fully understand, but that needs more attention and development, so I don't have a direct answer to that. Yeah, Chris?
The use of phosphor that can be excited in the visible to look at.
Yes. Yes, that would be, of course, a possibility that you change the phosphor. The question was why staying with the phosphor to be excited in the UV? Why not using one that is excitable in the visible? That can be a solution. That's something we have not yet done, but that's of course a good idea. Okay. So with that. We switch to chapter number 7 and leave the surfaces and go back to the gas phase. where it's about concentration measurements. And by that, we have the chance as well to repeat some of the measurement principles that we have seen already for thermometry. Repeating them is for sure not a bad thing to do. Okay, so it's about gas phase concentration measurements. Why is that important? Of course, if you want to study a combustion system, the scalar field, as we have seen, is very important. And the scalar field is not only temperature, but due to combustion, the concentration of species change. And that is something, of course, we are interested in to understand. Target species or parameters are, for example, mixture fraction, like in partially premixed or non-premixed flames. In premixed flames, it is the reaction progress that is of high interest. In both cases, non-premixed, partially premixed, or completely premixed, intermediate species are of interest, and of course, pollutants. And the list can be, of course, extended here. It's very important to note that whenever you do whatever technique you use to measure quantitatively species, then you need to know as well the local gas temperature. For a very simple reason. When the temperature changes, you have a change in the density. And you need to correct your signal, which denotes the concentration. This needs to be corrected for the local density. Yeah? Because if you have a change in your signal for a certain species, let it be LIF, for example, looking for a species like NO, the signal can change because of the concentration. But if you have as well a change in the or variable temperature, which you have, then you have a variable density, and for a fixed probe volume, which is given in an experiment, then as well, only due to the temperature change as well, the signal changes. And that's why you have to correct for this effect. And so there's no other way, I would say, as directly as well, measure simultaneously the local temperature. I say this is the best option. Sometimes maybe you have good reasons to say that you know the temperature, maybe in an adiabatic flame, in the post-flame region, where you can neglect heat losses. Then from simple calculations, you can have a good estimate of the temperature, assuming adiabicity. That is, in some cases, okay, but if you have to somehow justify that. Without justification in a paper, I would directly reject that. Yeah? You have to consider that. And I stress that point explicitly because sometimes it seems to me that it's not so clear. So you need to know something about the temperature, and the best option is measure it. We again have here different options. And we will see laser absorption spectroscopy will be critical. Laser-induced fluorescence, we will see, is again critical because of electronic quenching. And that is why most of the chapter is about Raman spectroscopy. I would like to share some more details about the technique. Okay, laser absorption, a reminder of what we have discussed earlier this week. You have a laser that is tunable. You measure the incoming intensity, and after a certain path length, you measure the outcoming intensity with a detector that is sufficiently fast to follow the change of the wavelength by that laser. Based on the Beer-Lambert's law, shown here in its simplest form, you can measure these intensities by the detector after the transmission. The initial one, you have to know the length, we discussed that. You have to know the absorption cross-section, and then you can directly deduce the number density of a molecule in a certain quantum mechanical state, here denoted by J. The problem is that along the laser path you have no resolution. It's a line of sight method, and if you have any inhomogeneity along this beam path, then you would not register that. And over that, of course, that will give systematic errors. However, it's a calibration-free technique, as we have discussed, when you know the path lengths, when you know the cross-section. But in turbulent flames, you do have inhomogeneities along the path. That's why it is not so well suited. It is well suited in environments and combustion where you have homogeneity. Let's say in a gas turbine at the end of the combustor. That's maybe there it's okay. Or in the exhaust system. And there it is really a powerful technique, especially for investigating exhaust pipe flows, where most often people have used tunable diode lasers. Yeah? Because those components are robust and have been developed for telecommunication purposes, but in the recent years, the last 10 years as well, we have seen that these diode lasers have been extended not only to work in the near infrared, but as well in the mid infrared. But here's an example where water is traced by a DFB diode laser operating in the near infrared in a region where as well telecommunication takes place. So what is done is you have such a diode laser. You based from a certain temperature stabilized system. You then change the laser current, and with the laser current, as you will see here, this is cranked up in a linear way. The wavelength follows, that is changed, and that is shown here again in the spectrum. So what you do is you change the wavelength, and the power measured by this detector here is given over here. Now you tune further on. You tune over the first resonance, and then you see the absorption signal appearing here. So as an order of magnitude, the best you can achieve in changing from this baseline dashed to that tip here is in the order of 10 to the minus 6. So that is the limit that can be measured in current systems. And then the information about the concentration and the number density, the concentration comes with knowing the temperature and the pressure, is from this area here. I just flipped that, and instead of using the time over here, sorry, that's in German, you can of course transform the time into a frequency, and the frequency is here given in wave numbers, in relative wave numbers. And now what you do is, in connection with the ideal gas law, knowing the temperature and the pressure, then you can deduce the concentration from this area over here. And that's a very robust technique. It's accurate, and it can be as well very precise. So the only drawback is that we do not have any resolution in line of sight direction. That's why already for thermometry we have discussed laser-induced fluorescence. Again, a reminder how that principle works. You need a tunable laser as well. It must be tunable such that the photons do have exactly the energy to bring up the molecule from this quantum state in this electronically excited state, as done here. Then you might have in the upper electronically excited state some relaxation, shown here by the yellow arrow. But of course, you will have as well direct fluorescence back, that is called resonance fluorescence. However, I have shown here the process after some internal relaxation, where this energy gap is dissipated into heat by, in the end, into the gas, into the surrounding. And then eventually you have here the fluorescence process that is then captured and monitored by a photomultiplier tube or intensified CCD camera or CMOS camera or so on. So most of the times you observe that redshifted, meaning that the wavelength of the emission is larger than the wavelength of excitation, and the opposite holds true for the frequency. Important, this state from which fluorescence takes place is an allowed state. So the system exists there for a certain time. For example, if you have OH and excite that to the first electronic state, the A state, then the lifetime, the natural lifetime, assume an OH molecule on its own in the vacuum, you excite that, is in the order of 600 nanoseconds. If you put the same OH molecule now into a flame at atmospheric pressure, 2000 Kelvin, then the lifetime reduces to something like 2 or 3 nanoseconds. And the reason is collisions. Yeah, this excited molecule is hit by other molecules, and with a high probability, they take away this excitation energy After this collision, these colliding molecules are possibly faster, or they have a higher energy with respect to the internal degrees of freedom. However, that molecule cannot fluoresce anymore. And that is the problem. And this is expressed in this formula over here. You're measuring the fluorescence intensity locally, and this is as well very sensitive. It is proportional to the number density from the initial state. That is what we want. That is the parameter of interest. You have to know the absorption. You have to know the cross-section. You have to know the overlap. I explained that already 2 days ago, I think. The overlap between laser and absorption line. That is a convolution hidden in here. The laser intensity. You have to know the probe volume size, the detected angle, the detected angle, and the detection efficiency of your detector, quantum efficiency, as well transmissivity of your optics. But as well, you have to know the spontaneous lifetime. That is a constant for many molecules and states that might be known. But the problem is the total lifetime. And so you have here two unknowns. One is your parameter of interest, but as well the total or effective lifetime is unknown. And as you have only one measurement over here, even after calibration where you take care of all these parameters over here, have measured the laser intensity, know the cross-section, know the convolution between laser profile and absorption profile, know the spontaneous lifetime, you still have these two unknowns. And that needs to be handled somehow. We have seen in thermometry, you can come that over or overcome that by taking a ratio of two lines, where then you hope that these lifetimes are close to each other and cancel out. But in concentration measurements, you have to do something about it. And we discuss in a second different methods, none of them is perfect, how to solve that problem. Okay, so here you see again the experimental setup. You have the tunable laser that can be, for example, a dye laser, with which you then excite the molecules over here, and you image them onto either an array detector or a point detector like a PMT with a certain lens system, and as well typically a filter that any other light than the fluorescence light is rejected. So you have a good spatial resolution because of this 90-degree arrangement. It's very sensitive. So in principle, you can go as well for intermediate species. OH is one example. But formaldehyde is as well an example that is built as an intermediate in combustion of hydrocarbons. In any case, you need a calibration. Why? Because this probe volume size, the detected solid angle, the detection efficiency are typically very, very difficult to obtain unless you perform a calibration. A calibration means you have a gas sample with known concentration, pressure, and temperature, and know everything else in this equation from which you then can deduce this quantity. But as I said, the total lifetime is the problem. That is typically unknown. And here is some more detail from which parameters this total lifetime is composed. So first of all, you see here we have a dependency on three parameters. First, the so-called Einstein A coefficient, which is nothing else than the inverse spontaneous lifetime. So this is for a given molecule, for a given electronic state, a molecule-specific quantity. And for some molecules, we know that. So that is given. Then a second parameter shoots up. This is the predissociation rate. So some of the molecules, upon excitation, I make here a drawing. This is the energy of a molecule over the distance between the two nuclei. We are talking about diatomic molecules. You have here the electronic ground state, denoted by large X. You have here the first electronic excited state, A. We have here different vibration levels. I cannot fill up the rotational levels. They are too thin to each other. So we know they are there, but we neglect them for the moment. And then you might have here your excitation, and you want to have then, maybe after some relaxation, here your fluorescence. But some molecules do have as well a crossing potential that is repulsive, something like that. That's as well something which is specific to molecules. Some have that feature, others not. And this is a potential that is, as I said, repulsive. And if the molecule, and that can appear suddenly, spontaneously, change from this binding potential to this repulsive potential, then the molecule dissipates. Why that? Because there is no local minimum, meaning that the lowest energy is achieved for very large distances between the two nuclei, meaning it's dissociated. And if that happens, then you have a predissociation rate which has a certain value. And then the third, this is the quenching rate, and the quenching rate depends on the gas matrix, the pressure, and the temperature. And maybe we can get a certain understanding of that. Let's say we take OH, which has been electronically excited after absorption of a UV photon, and now it collides with a species, let's say M, as a collision partner, and then the OH is de-excited, so meaning OH without any star. The star was for the electronic excitation. And then you have here afterwards the colliding molecule with a different energy. And this different energy can be in translation, or the internal energy has changed. And this is depending on the collision partner, thereby the gas matrix, the pressure, because the higher the pressure, the higher the probability for collisions, and as well the collision rate increases with the temperature. So that's why quantitative LIF is challenging. You must somehow treat this effective lifetime. Now, I will discuss 5 possibilities, and again, none of them is the solution. It depends now on what you're after and what you can afford. Maybe the most accurate way is that you, in a separate experiment, determine the lifetime of the species you're interested in. For example, OH, for example, CO, for example, NO. For these molecules, it has been done. So what the people have done, they have, let's say, take CO. That's easier than OH, because OH you can't take from a bottle, a gas cylinder. You have a certain gas cell where you put your CO in, where you control the pressure, the temperature, the colliding species. And then what do you do? How do you measure lifetimes? Maybe that's a question that you could answer if you think back to the phosphorescence. How to measure lifetimes? You just need what? Any idea? A PMT, that's already a good thing. It must be a fast detector. But if the lifetime is, let's say, in the order of a couple of nanoseconds, what do you need for excitation? Would be a normal nanosecond laser a good choice? A picosecond laser, yeah. Maybe even better, a femtosecond, but if you go to femtoseconds, then it's spectrally broad. Yeah, and that's why using picosecond lasers, where you still can excite single transitions, and then look for the decay of the fluorescence. Identically like in phosphorescence, but much faster. Maybe I should make a short drawing, and I will remove it afterwards. So we are now in the scale, let's say, of 10 nanoseconds. And there you would like to have still something like a delta-like excitation. And that brings us to picoseconds, let's say 50 picoseconds or so, to then, after that excitation, observe this exponential decay. And from this exponential decay, you get the lifetime. And you repeat that experiment for different colliding species. This is this vector C. You put in CO2, you put in N2 with all, of course, controlled and known conditions. You vary the temperature and you vary the pressure. And then you end up with a large set of data that allows you to control that parameter. But then, even if you have done that, in the actual measurement, you need to measure then as well, of course, temperature, that's anyhow necessary, pressure as well, it's maybe not so critical, but you have to measure then the species concentration simultaneously. So if you want to, that's the best way to do it, let's say. If you want to make this quantitatively and make use of these separate measurements that has been performed in a cell, then you need to know for your actual measurement that species concentrations. And that has been, we will see that later in this chapter, that can be done by combined Raman-Rayleigh scattering for open flames. But it's a huge effort. It's a huge effort. And that's why there is only very, very few people doing that in that way. Rob Barlow in Sandia National Labs, for example, he is performing Raman-Rayleigh measurements to get the main species and the temperature. And simultaneously, he performs CO-LIF, and he can then correct, by using this data, the CO measurements based on that information. So that's a huge effort. Okay. After that, what can we do as well? Another possibility, which is much more pragmatic, is to say, well, we do a good calibration where we have the measured fluorescence signals and relate that to that number density we want to measure. And our calibration constant contains not only the probe volume, solid angle, detection efficiency, and so on, but all these effects of the effective lifetime, such that you have to perform this calibration in, for example, laminar flames, where you know the conditions, and then the actual measurement, which is not a laminar flame anymore, but having the same equivalence ratio, that can work as well. Yeah, that's much easier, but it's restricted to situations where the chemical conditions between calibration and actual measurements have not changed. Yeah, so for premixed flames, for example, that seems to be an alternative. For non-premixed flames, it will be more critical, I would say. Some people have said, why not doing saturated lift? Because that's not a really a good choice. I will not detail it here. So, but you should have heard about it. Let's, for that reason, switch to a fourth possibility, where fluorescence is combined with absorption. I will not derive these equations here. I will instead try to give you the principal idea. So we have seen absorption spectroscopy is a very strong tool because it's free of calibration and gives you along a line of sight number density. Yeah? You do not know where you have had high concentrations and low concentrations. Maybe that has changed. But you know relatively precisely and accurately the total number density along that absorption path. If you combine that now with fluorescence along that line, then the idea is that the fluorescence gives you the information about where the species have been higher concentrations and lower concentrations. Yeah? And that is valid only if along this 1D volume the quenching has not changed drastically, of course. Yeah? So in the post-flame region, for example, that is a possibility by a simple extension, measuring the ingoing intensity, measuring the outgoing intensity, to get an estimate of the concentration along that beam path. Okay. And I refer to publications where that has been derived. So what is the important quantities? T stands here not for the temperature, but for the transmission. So this is the outgoing intensity over the ingoing intensity. Sigma, again, is the cross-section. And this quantity V over here is defined over there. That is calculated basically from the local fluorescence. F is here the fluorescence intensity at a certain location. And you see in this definition here, integral from 0 to x and 0 to L, L being the full length of the line of sight. So if you're interested in that, I refer to that publication here, where it has been shown first. For some applications, it might be a good choice. But as I said, it's important that along the line of sight, along the laser path, the effective lifetime is not changing too much. You don't need to know it because it cancels out in the derivation. But if it varies strongly, let's say from over a flame front or so, then this technique would not be applicable. Okay, here's a question.
Could you combine that possibly with PLIF, like where you kind of use a laser exhaust, the absorption spectroscopy to like kind of get a line to calculate that total time that you can then apply to your whole field? Or in a turbulent flame application, would you expect the total light time to vary too much over the laser volume?
I'm not sure whether I completely understood the question. The question was whether you can apply that for a turbulent flame where you have a temporal variation.
Well, so in this example, my understanding of your example is that you're doing 1D lift.
Yeah.
And then also laser absorption spectroscopy.
Combined.
On the same beam path.
Yes.
So my question is whether you could expand the lift to plane
Okay.
and use your
Okay, got it.
absorption spectroscopy to calculate the total lifetime to apply to the whole plane.
But the question is, okay, maybe there are two questions. The first question, whether you can expand that from a line to something like a plane in a turbulent flame. Maybe I should make a short drawing for that.
For the lift, not
For the lift, okay. Just to be sure that I got your question correctly. So we have here the laser. We expand that, we collimate that, we make something like that. Then we measure the, let's say, PLIF over here. If you combine that, then you would need as well to measure the laser intensity along a line here and along a line here, such that you know for each row of pixels the absorption. In principle, that is a possibility, but if you have strong turbulence, you have beam steering. What do you do if a beam, maybe I should take a different color, just to exemplify that. If, let's say, one part of the beam is doing that because of beam steering, so be careful. In principle, yes, but beam steering can kill you. And that's maybe better to use something like a comb in space, where you have multiple 1D things, and then you can see them, how they develop, and beam steering is directly visualized at the PLIF camera. So that's one thing. Yeah, people have done, I know from the DLR, for example, in Cologne, where they use that to do measurements in the exhaust of a gas turbine combustor without taking too much care about the beam steering, because they assume that it's more or less homogeneous. But this assumption might be okay. The second question referred to lifetime.
Well, that basically answers
That answered the question already. Okay. Good. Then the fifth possibility, we already discussed that some radicals, like the OH, show here potential curves which are repulsive. The lowest energy, that's always what nature wants to have. Once they are on this repulsive potential isosurfaces, the lowest energy level will be for large internuclear distances, meaning the system, the OH radical, would have dissociated. So upon excitation into a certain level in OH that is very probable for the third vibrationally excited level, there is a spontaneous crossover to these repulsive potential surfaces, such that this number P, the rate of dissociation, is relatively high. And people have used that for atmospheric flames because then the pre-dissociation rate is higher than the quenching rate. And if this is true, you just say, well, then I just cancel that, and I have here only remaining quantities which are molecule specific. They're not dependent on the environment. Good idea. What is the drawback? If the quenching is very, when the pre-dissociation is very probable, you have a weak signal. Because then this pre-dissociation rate as well de-excites the molecule. It will not fluoresce, and thereby your fluorescence intensity goes to 0. You can compensate that in principle by pumping harder, but that's not a good idea, because if you pump hard, then you change the population density from the initial state. Okay, then you bring up, let's say you have pumped from the J level, rotation level 7 or so. Maybe you have taken the Q line from J7 to J7 in the electronics excited state at V equals 3 up there. then the population will decrease and decrease strongly, and that means you're again intrusive. So that's as well, that is not really a good choice. But it has been used, and you might come over that in articles where the authors have been excited about that, and maybe you have missed then the literature later, which more critically evaluated that method, and by that I would like simply to warn you. Okay, so that's why, again, we come back to these non-resonant techniques. And these non-resonant techniques are Raman spectroscopy, which is very often combined with Rayleigh spectroscopy. We have seen that yesterday and the day before, what the difference is to a resonant technique. So what you have here is a laser frequency or wavelength that, again, this is the energy in vertical direction, where you do not hit any resonance, where you do not have an absorption to a level which has a certain lifetime, but you have, in this view, this representation, you bring up the molecule to a state which is sometimes called a virtual state. It is not allowed, it is not existent. The lifetime is nearly zero, from which then the molecule instantaneously returns back to the initial state. Then the emitted radiation has the same frequency. That is an elastic process, and that is termed Rayleigh scattering. Whereas with the probability of something like 1,000 less, to give you a number, the molecule eventually might return to a higher vibrational rotation state. And that is then here an inelastic scattering process, because the exciting and the scattered light do have different frequencies or wavelengths. In this case, where you have Stokes scattering in Raman, you leave behind the molecule in a higher rotational vibrational state than the initial one. Or if you start from an excited level, you can bring it further down, where you have then anti-Stokes, where now the radiation has a higher frequency or a lower wavelength than the exciting one. And here I should once again very clearly point out what the difference then is in terms of quantification. This virtual state has something like a lifetime, let's say, of 0. Yeah, I directly take a small number, 0 femtoseconds. It's really short. It's so short that there is no chance for any collision, even if you go up in pressure. Yeah, for the pressures we are interested in, for sure, that there is no collision such that this process is independent of the gas that surrounds it. And that is the important difference. Yeah, it is not going from an allowed eigenstate where collisions matter. It is an instantaneous process. And that is now to be used for quantitative measurements in gases. And I see the first hour is over. Maybe it's a good time to make a break and meet again at 10:05 and then have a closer look into this Raman-Rayleigh process. Thank you very much.